Hello everyone. Last time we looked at vectors geometrically. This time we are going to look at vectors algebraically. Are you ready? Let's go. Let's start with the Cartesian coordinate plane. We usually call this the xy plane. And we now take a vector v, put it in the plane so that its initial point is at the origin, like this. Notice that the terminal point AB determines v. And we write v as AB. We say that this vector is in the standard position. And when a vector starts from the origin, we call it a position vector. Here are a few examples of position vectors in the xy plane. Okay, let's continue. So that brings up a question for us. Given 2 points P and Q in the plane, how can we write the vector PQ in the standard position? Well, we can do a translation of the vector so that it starts at the origin. In other words, we are moving the vector to the standard position. How do we do this algebraically? To move P to the origin, we can subtract x1 and y1 from its own coordinates so that now the initial point is the origin. And to move the vector, we also need to do the same to Q. So now the initial point is at 0, 0, and the terminal point is at x2 minus x1, y2 minus y1. And thus, we have PQ in the standard position. Notice that you can think of this as Q minus P. We call that geometrically. Two vectors are equal when they have the same length and same direction. What can we say about equal vectors algebraically? We say that two vectors, u is equal to AB and v is equal to CD, are equal if and only if A is equal to C and B is equal to D. For example, if we have 3m, 4n is equal to negative 27 and 16, then 3m must be equal to negative 27 and 4n must be equal to 16. So m is equal to negative 9 and n is equal to 4. Now let's talk about how to compute the magnitude. Here we have the definition of a magnitude of a vector. By the way, in printed media, we often use boldface to indicate a vector instead of drawing the arrow on top of the letter. This definition should not be new to us. If we draw a new position vector in the plane and try to find its length, we are using the Pythagorean theorem. See that this is also the distance formula. So if we have a vector not in the standard position, say PQ, where P is x1, y1 and Q is x2, y2, then the magnitude of PQ is given by this formula. From the previous episode, we have talked about how to add and scale vectors geometrically. This time, we are doing vector operations using coordinates. So how do we do scalar multiplication? It's actually pretty straightforward. Suppose u is equal to AB and k is a scalar, then ku is just ka and kb. That means we are multiplying each component of the vector by the scalar. For example, if we multiply the vector 3, negative 2 by the number negative 4, then we have 3 times negative 4 and negative 2 times negative 4. So we get negative 12 and 8. Another vector operation is vector addition. Also straightforward. If you have u is equal to AB and v is equal to CD, then their sum is a plus c and b plus d, which is just adding the corresponding components. Here's an example of vector addition. The 3 plus negative 5 gives us negative 2, and the negative 2 plus negative 1 gives us negative 3. We can understand why the definition of vector addition works by seeing it geometrically. Suppose we're adding two vectors, u and v. So we get this u plus v. Now, since u is equal to AB and v is equal to CD, we can see that the x component of u plus v is a plus c, and the y component of u plus v is b plus d. So far, we have been talking about two-dimensional vectors. You may ask, what about three-dimensional vectors? Turns out that all these things that we have done can be extended to three-dimensional vectors. Here, I have listed a few of those concepts. There will be more on vectors. Stay tuned. If you like this video, please give me a like, subscribe to my channel, and share my videos to others. It will give me support to make more videos. Thank you for watching this video. I will see you next time.